All right, so what I want you to do now is visualize this situation. Let's say we have two slits in metal, and let's say that we have light, and this light is heading towards these slits. What will happen as they pass through the slits here? Well, we might say, well, we'll probably see something like this on if this was a wall over here or the floor. Probably see something like this. Well, that could be true if the slits are really, really wide. But even if they're really, really wide, we're still going to have this kind of strange effect. And so, there's been a lot of different thought experiments through history in physics, and these were, made pretty popular by Einstein's theory of relativity. Really interesting things thinking about, if relativity is true and time slows down and that kind of thing. But even further back, I think about what Newton thought about. He said, light must be a particle. It goes in straight lines. But through the years, they discovered that light does some strange kind of things. And so, figuring out actually what light is a big part of the history of physics, and really had a pretty big impact from the time of Newton onward. Huygens said that, and his proposal, what was happening was that every point source or every point on a wave acts as a point source. So if you have a wavefront like this, and the solid blue line here represents a crest, there's actually in every single spot of this, there's a point source. And so we have all of these, crests, mini crests kind of coming from it, extending outwards. And this was a, kind of a wave nature looking at light and, describing it based on wave properties. This may be a little bit more helpful picture. Let's say we have, these gold lines represent crests. And so the source would be like here, and the crest would reach out, fully out to here, and so on. And so if, let's say you had, a spherical wavefront here, that's representing the crest there, and every single spot represents a wavefront. If it's like that, then we can start to talk about how, light acts like this as a wave. And it turns out light is a wave, and Newton was technically correct too, because light is also a particle. It has momentum and it has energy. It has no mass, but that's for another time. So what we actually see, the light's going through the slits. This is what we would think, like, oh, if they're just straight lines, they're just going to do that. But this is actually what happens. The light spreads out, and we have these destructive and constructive interferences happening here. And this is kind of strange. This is a nice example of a wave that enters a section where, there's a small opening and the waves diffract. And so this is water. This is water going through here. And you can see the crests pretty well here, like right here, right here, right here, and so on. And, these form out across, and kind of went across there, but yeah, that's happens with mechanical waves. It turns out light does the same thing. So diffraction takes place when a wave with a wavelength comparable or larger than the size of an aperture or an obstacle moves through or past the aperture or obstacle. And so the wavelength, right, from a crest to a crest, needs to be comparable to the opening. So if this opening right here is comparable, you can have pretty good diffraction effects. If you look over here, this length is pretty large, but you still see the diffraction here. You see these, curvy patterns happen. And so this is a ripple tank. This is, waves going through an opening, and you can see what happens to the shape of the wave as it passes through here. So now what I want you to do is watch the rest of that video, the Veritasium. You can go on YouTube and type in interference with water or light interference and watch that entire video. It does a really, really good job showing the kind of what we've seen so far and connecting that with light. This is kind of a neat picture here. We have waves passing through, waves diffracting here. We have waves diffracting over here. And as these waves interact with each other, we have a point source here, we have a source here. And just like we had before, we're going to have areas where there's crests and crests. And then we're going to have areas where there's troughs and troughs. And then we're going to have areas where there's crests and troughs. And so if we have two sources, they can interfere with each other. And that's what we see. If we have light passing through, if you have, coherent light coming through over here and coming in and through a couple of openings, it diffracts and we get an interference pattern. There's places where there's constructive interference. There's places where there's destructive interference when it hits. This is a good simulation in PhET. Where if you look at wave interference, you can actually see with multiple sources or even a single source this happening here. So what do all these things have in common? Well, you think about this as a water wave. This is producing sound wave. This is producing light wave. They're all producing crests and troughs of waves, right, as they go out. And so what happens if you put two of them a certain distance away from each other, and then the waves go out? You're going to get the interference, constructive and destructive interference, like we talked about earlier. So let's go ahead and just practice a interference situation at this point. So let's say that we have a crest and a trough coming together. Go ahead and draw out what the resultant will be, and then yeah, and what will happen there. So go ahead and pause the clip and give that a try, and when you're ready to check, you can hit play to continue. Okay, so in this case here, you've got the positive amplitude there, you've got the negative amplitude there. When you bring those together, we add them together, A plus B, positive 1 plus negative 0.5 would be positive 0.5. And so they're going to destruct. And then remember, after they destruct each other, then they're going to continue like nothing ever happened. That 1 meter amplitude wave is going to continue like this, and then that negative 0.5 is going to continue like this, like nothing happened. Now, obviously, with friction, so those amplitudes could get less over time. So here's that picture again of the waves going through and diffracting, waves interfering. And so what we have, in this case here, we have two openings, and you can see the crests from this one, and you can see the crests from this one. And then what happens is the crests and troughs can line up, and then you'll also have destructive interference. And if you can see here, if you continued the waves, from this one and this one, right here in the middle, there's a crest and a crest, and then a trough and a trough, and a crest and a crest, and a crest and crest, and trough and a trough. Constructive interference all along this. Now, if you look at the wave from here to here, and then the wave from here to here, this is all destructive interference. And so you see how it's kind of dim along this, and dim along this, and dim along this. That's because the path difference is 1/2 different. The wavelength is 1/2 different, and so you have destructive interference. Okay, so again, we can see the lines of destructive interference there along, these right here, this right here, this right here, this right here. All right, so what I'm going to have us do here is draw out the light coming in and then spherical set waves, not spherical, really cylindrical, but you know, the coming out like this. And so you could draw those like this, and then one like this, and equal wavelengths, right? Now at the very same time, you're going to have not only these, but these, right? So you can draw these, right? One here, one here, one here. And so what happens is when these overlap, you're going to have sometimes crest with crest and sometimes a trough with a crest. And you end up getting interference. And so what this will look like is, you know, along these lines, right? The crest and a crest, and crest and a crest, crest and a crest, crest and a crest, crest, crest. These are all in phase. And these lines lead to where there's constructive interference. And this is actually what you'll see. The light comes through two slits. You have a bright spot in the middle, then you have another bright spot and another bright spot. And then it turns out to be darkness in between because you have a crest and a trough and a crest and a trough and a crest and a trough. And so you have complete destructive interference. And then in between you can have a little bit of light, you know, but it won't be as bright as when they're both, you know, in phase. And so, yeah, so we have our constructive interference at these different locations. And these are integers. N equals 0 is the very center part here. And then the first integer 1, where the path difference is 1. Integer 2, where the path difference is 2. Exactly 2. You know, so the wave, this wave from down here has to travel exactly 2 wavelengths more to meet this one. And then you have constructive interference and so on. So you'll also want to draw this out too. There's fringe spacing. We call these fringes, where we have bright spots. S is the variable that we use for fringe. And so from the middle there to n equals 1. Lowercase d represents the distance between the slits, the distance between the centers of the slits. And capital D represents the distance from the screen itself. And we have that. And then, so what we have then is an equation that we can use, and we see this under 4.4, where we have all of our different variables. S is the distance between the fringes. Lowercase d is the distance between the slits here. Capital D right here is, you know, how far away we are from a screen. And lambda is the wavelength of light that's coming through.